Isopic line actually is about the linear line of objective function. Isopic line is about the linear line of objective function. If the problem is maximization, we call isopic line. On the other hand, the problem of minimization, we call isocost line. Okay, so it's the same thing. Isopic line for maximization, isocost line for minimization. And this is the linear line of objective function. So for the isopic line, firstly, the first thing that you have to do is to draw in the graph of objective function. This is the isopic line. So if we ask you to draw in the graph of this one, profit equal to 7x1 plus 5x2. Can you draw in the graph? Profit equal to 7x1 plus 5x2. You cannot, right? This is because you don't know about the profit. But this line we call isopic line. We need to draw the line. So which means that in order to drawing the isopic line, you need to assume the value of objective function. You can assume any value that you want, but just please make sure that once you assume the value of objective function, when you draw this line, is still in the same scale that contained in this axis. So for example, if I want to draw the isopic line in this case, I can substitute any value to the profit, but I need to draw this line within this axis. So you might think about using the number that's come from using the coefficients in front of x1, x2 multiplied together. Let's say it can 35 to be the profit and drawing this line. That's okay. But since the scale in this axis is like up to 100, if you're using the profit to be 35, when you're drawing in this axis, it's gonna be very small. So for me, then I'm just, okay, let's say that I assume the profit to be 350, and I want to draw this line. So I assume profit to be 350, and then I'm drawing the line of objective function. So this is my isopic line. And again, you cannot, using just the 350, you can change to other value that you want. You might prefer 400, 500, or maybe, let's say 600. It depends on you. It depends on the user, but just make sure that it can contain within this scale of the axis. But for me, let's say I assume using the 350 and I'm drawing this line. So it means that if you assume any value that is not 350, you're going to have another line that we call the same way isopic as well. Right? So in conclusion, it means isopic can have like a million of line. It depends on the value that assume to substitute to the objective function value. But one thing that you can see, it doesn't change, we are not changed about the coefficient in front of x1 and 2. So in this case, if you assume to be other value, just as 210, we have this line, 350, we have this line, 420, you have this line. All this we call isopic line. But we want just the one line to be your isopic line. Let's say for me, I use 350. And you can see all have the same slope because we change just the value, that constant value. We are not change the coefficient. We still have the same coefficient, which means we have the same slope. And once you drawing only one isopic line, let's say this is for me. What next? Based on the previous one that I just showed you, you can see this is for 210, 350, 420. If we argue about 600, what's going to be? Should be like this, 600, 800, 1000, 100 maybe around this. You can see that if you increase the profit, or increase the objective function value, the line is shifted on to the right hand side. If you reduce the value of profit, let's say from 250 to 210 to 120 to 50, the isophysic line is going to move coming to the origin point. So based on these things, we can see that, okay, if we have just the one isophysic line, I have 250. And we know that if we want more profit, the line is going to move to this direction. If you want less profit, the line is going to move to this direction, right? So if we have just the one line, we can find a solution. In this case, we're drawing this line. This is my isophysic line, have one line. Then you're using the ruler, right? Or maybe student ID card. When you do the exam, it's emergency. You don't have any ruler, so what thing that you can use, and it's not illegal. So it's student ID card. Just cover the line. Maximization. You move to the direction that out of origin point. Minimization, right? You project or move the line coming to the origin point, right? The point that provides the optimum solution point is going to be the last point of physical area that your isophysic line is going to contact before it out of physical area. Remember, for this problem, this is my physical area. This is my isophysic line. I cover the line. And then maximization, I project the line in the direction that out of origin point. The last point that I can contact before the line out of physical area is this point, right? So this one is going to be the optimal solution. So this is the way of using the isophysic line. Just drawing the graph of objective function, and then cover the line, and then you project or move the line to finding the point on physical area that you can contact, right? The farthest one before you out of physical area from the isophysic line. So in this case, right, it's going to be this point. So the intersection point between the first and the second constraint, this is the answer. This is the answer. Optimal solution. And we already find the coordination, right? Cutting point between the first and the second constraint is x130 into 40. And this is the isopropyl line. Okay? So before we doing the practice problem, you need to understand something referred to the physical area aspect. From the previous example, the physical area that I said the area of the possible answer is body area, right? But actually, it depends on the type of the constraint. Sometimes your physical area is not an area, but it's going to be the point or line. For example, if I'm using the same example, but I change something. Look at the constraint. Carpentry and painting constraint. Now, the signal of the constraint change from less than equal to be equal. So the meaning is changed. Because the previous one, you have less than or equal, right? So it means that you can use up to this available carpentry hour and painting hour, but you cannot using more than this one. But you can use less than this one. But in this case, if the constraint is to be equal signal here, it means that you need to use equally to the 40 and 100. Use all of it, right? And in this case, let's say that when we try to solve the problem using the graphical, remember the first step, we drawing the graph of all constraints. So this is the graph of the first constraint. We drawing the graph and then no shading because this is equal. This is the second constraint, no shading. When we move to the second step, trying to find the intersection area that we call the physical area. Now physical area is just the intersection point. Right? When you assume isophysic line, you can find the answer. Okay, this answer is on this point. But the key point of this slide is mean that physical area, no need to be the area, it can be just only the point. Or another example, if I using the same example, but I change just only one constraint. The first one is still less than or equal, but the second one is using equal. So what happens if you solve based on the graphical method? The first constraint, this is 1. And then less than or equal to net 40, right? So then you shading below the line. Then you drawing the graph of the second area, this one, no shading. So what next when you try to find the physical area? The intersection area is going to be this part of the linear line or the red line. So now the physical area is just the line, not an area, not the point, but this is line. Okay, so it can be anything, area, point, or line. The next one is that, okay, let's practice for minimization. Suppose that this is my linear programming model. Now I have the problem of minimization. TC stands for total cost. So we would like to minimize the total cost equal to 4x1 plus 5x2. We do have two constraints. x1 plus 2x2 greater or equal to 80, and 3x1 plus x2 greater or equal to 75, and don't forget the non-negativity constraint. x1, x2 greater or equal to 0. So if I try to solve this one by using the isophysical line. So the first step, I need to drawing the graph of all of this constraint, right? The first constraint, we try to find x1 and x2 intersection. x1 intersection, we substitute x2 to be 0, x1 cutting at 80. x2 intersection, we substitute x1 to be 0, we have 2x2 equal to 80, so x2 cutting at 40. Then you have this one, the line of the first constraint. But since the constraint is greater or equal, so when you shading is above the line. This is the first constraint. The second constraint, we do the same way. We try to find x1, x2 intersection. x1 intersection, we substitute x2 to be 0. We have 3x1 equal to 75, so x1 cutting at 25. x2 intersection, we substitute x1 to be 0. We have x2 cutting at 75. So this is the graph of the second constraint. And since it is the greater or equal signal, greater or equal to 75, so then the second constraint is also shading above the line. But then we try to drawing these two constraints in the same axis. So this is our first step, drawing the graph of all constraints. We finish. The next step is that we try to find the intersection area of all constraints, right? So in this case, the area that should be intersection area that we refer to be the physical area should be this area, right? So then we shading this one. This is our physical area. What next? We just try to draw the graph of this objective function. We call iso cost line. You substitute some value to be the total cost and drawing this graph. Let's say that I substitute some value, maybe 400, I cannot remember because I didn't write it down. And drawing the graph, I have this dashed line to be my iso cost line. And then what next? I'm just using the ruler cover the line, right? And right now, the problem is minimization. Remember minimization, we project the graph, the iso cost or iso profit coming to the origin point, right? So now we project this one in the parallel relation coming to the origin point. The last test point of physical area that we can contact before this iso cost line, right, out of the physical area should be this point. So this point is going to be our answer or optimal solution of this problem. So then this is optimal solution point. Then we solve for the intersection between the first and the second constraint. We have the coordination x1 14, x2 33. We substitute x1 14, x2 33 into the objective function. Then we have the total cost is equal to 220. So this is the solution. Okay. Next. All of this that can just show you the maximization problem and minimization problem. Both are just the very basic problem. We do have another special case for linear programming. The first one we call alternate optimal solution. As the name states, alternate optimal solution is mean you have more than one optimal solution. Look at this problem. Now we have the maximization problem. We want to maximize the total profit equal to 50x1 plus 75x2. We do have three constraints. I try to solve for this problem. Let's start with drawing the graph of all constraints. Try to find the feasible area or the area of intersection area of all constraints and substitute some value to be the profit, drawing the isometric line, and then we try to project to find the solution. So this is the solution. Three constraints. This is the feasible area. I assume some value to drawing the isometric line. The dashed line is isometric line. What next? Uncover the line, right? Maximization, we project in the direction that out of origin point. Right? The last point of feasible area that we can contact is not the point, but it is about this side, this line, this edge. So you can see every y is going to be this one because actually the slope of isometric line and the slope of the first constraint is the same. If you look at this one, if you use 25 divide for all objective functions, you have 2x1 plus 3x2, that will be the same slope. The slope of isometric line and the slope of the first constraint are the same. So that's why when you project the graph of isometric line out of the origin point to find the optimal solution, it's going to perfect match with the graph of the first constraint. And this one is going to be not only the point, but it's about the line that provide you the optimal solution. So it means that we have a million of optimal solutions. Every point that stay in this line between point A to point B, the red one, if you substitute into the objective function, you can have the same total profit, that maximum. So it means that we have more than one optimal solution. But in practical, the way that we answer, we prefer to use the corner, right? So we might answer point A or point B. Right? If we substitute point A or point B into the objective function, we have the same solution, the same profit. That would be the maximum one. So this is the alternate optimal solution. You can have the solution more than one optimal solution. The second special case we call degeneracy. From now to the next few weeks, when you see the word degeneracy, it means that we have something that's special to our problem that's going to violate about the rule that we can apply. For example, in this case, for the graphical method, you can see that based on 2 or 3 examples so far, the optimal solution is occur at the intersection point between constraints cutting together. Right? Just 2 constraints cutting together to be the optimal solution point. But the problem that we refer to the degeneracy case is mean that optimal solution will occur at the cutting point from 3 constraints cutting at the same point. So this is special case. We don't have the picture to show you because we cannot study this later on. But just want to inform you that degeneracy means optimal solution occur at the intersection point from 3 constraints cutting together at the same point. And how about the third one, infeasibility? This is the example of infeasibility. Okay, now we have the example of minimization, x1 plus x2. We do have 3 constraints here. And we try to solve using the graphical. We then perform the first step, drawing the graph of all constraints. But after that, when we try to go to the second step, right, try to find the intersection area of all constraints, we cannot find. Because there is no area that be the intersection from all constraints here. So you cannot find feasible area. If you cannot find feasible area, it means that there is no possible answer. So we call infeasible solution. There is no answer that's possible in this case, because you cannot find a feasible area. Okay? And the last one, we call unbounded solution. Look at this example. We have the maximization 3x1 plus 5x2. We do have 3 constraints as well. Then I try to solve it. Drawing the graph of all constraints, shading visible area, assume some value, and drawing the isomorphic line. The dashed line, the red one is my isomorphic line, right? And then this one is not. Let's see. Actually, there is no this. I don't know what. Yeah. Let's say actually we have just only this one. Okay. Okay. That's fine. Actually, there is no the blue line. There is no the blue line. So when you project, there is no the blue line. Okay, just the that's one. When you try to find the optimal solution, in this case maximization, then you cover the line. Maximization, you project to this direction, right? You can see that you cannot find the solution because you still have the area that you can go for. Because the area of visual is not the closed area. You can project more and more and more because you still have the area that you can go to. So we can imply that actually there is no answer. You cannot find it. It's called unbounded solution or invisibility solution, but in the case of unbounded solution, because this visible area, we don't have any closed area that we can find the optimal solution point. So all this is a special case. Okay? So we finished very basics one for linear programming, right? For the graphical. So then we're gonna spend this time right now to do the practice problem, just 2 or 3 practice problems together before we're going home. Then, so
Can I use it?
we have this 5 examples. I will not provide all the solutions for you, but we're gonna do together. And I show you the solution for you just 3 examples because the next 2 is the same. We can do the example 1, 3, and 5. 1, 3, and 5. So let's do the first one. The example, just warming up, it's very easy. You can spend maybe 2 minutes to finish. Example 1, right?
Huh?
We have the maximization z
Give me one more. It's sweet. It's really sweet.
5x2.
Thank you. If you don't like sweet, you don't eat it.
Subject 2, we do have x2 less than or equal to 6. This is the first constraint. 3x1 plus 2x2 less than or equal to 18 is the second constraint. x1 and x2 greater or equal to 0. So just warming up is a very, very easy one. What do we do for the next step? We need to setting up or construct the existing, right? So then we know that from the concept of graphical, we starting with the drawing the graph of all constraints. So we need to make the decision that about the scale for the axis. So in this case, I'm looking at the plan and think that okay, scale each for 10. That should be enough to drawing the graph. So we're gonna have like this one. This x1, x2, 0, 2, 4, 6, 8, 10. Two, 4, 6, 8, 10. So what next? we're gonna do the graph of all constraints, right? The first constraint is x2 less than or equal to 6. So we're doing the graph of x2 equal to 6 first, right? This is the graph of x2 equal to 6. And what next? It's less than or equal, right? So we shading below the line. When you shading, you just just using the arrow to show the direction. Understand? Please do not do the real shading, okay? Because let's imagine that we have more than two constraints during the exam that we have, right? I cannot see anything on this slide. The second constraint is 3x1 plus 2x2 less than equal to 18. So we draw in the graph for 3x1 plus 2x2 equal to 18 first. x1 intersection, we substitute x2 to be 0. We have 3x1 equal to 18. So x1 cutting at 6. And then x2 intersection, we substitute x1 to be 0. We have 2x2 equal to 18. x2 equal to 9. So then this is the graph of the second constraint. Cutting x1 at 6, cutting x2 at 9. And it's less than or equal, right? So we shading below the line. So we go to this direction. So this is the second constraint. So then, after we have this graph of the two constraints, we try to find the intersection area, and we shading that area we call feasible area, and this is the feasible area. This is a feasible area. The last step, let's say that we're gonna apply the concept of isoprofit line. So then I need to assume some value to be z value to drawing the graph of objective function to be my isoprofit line, and then I project the line. So let's say that I assume it to be 15. Let's say I assume z to be 15. And then I try to drawing the graph of this objective function. My objective function of my isoprofit line right now is 3x1 plus 5x2 equal to 15. Finding x1 intersection, substitute x2 to be 0. You have 3x1 equal to 15, x1 cutting at 5. x2 intersection, substitute x1 to be 0. You have 5x2 equal to 15, x2 cutting at 3. So then this is my isoprofit line. The isoprofit line right here. Have the equation 3x1 plus 5x2 equal to 15. Okay. And what next? You're gonna use the ruler, right? Let's say this is my ruler. Cover the line. Problem is maximization, remember? So maximization, we project the line in the direction that all of origin point. So we go to this direction. So the last point of visual area that we can contact before the line is out of visual area in this point. So this one, intersection between constant 1 and 2 is the optimal solution point. Actually this one. Optimal point. And we can find coordination, x2 to be 6. Actually, you substitute x2 to be 6, you get x1 equal to 2. So 0.26 will be our answer. So in conclusion, for this problem, x1 answer to be 2, x2 answer to be 6. And how about z? Z is 3 multiplied to plus 5 multiplied 6. You have 36. So very easy for the first one. Okay, so this is the first example. We're just warming up for review about the step, right? To do the graphical. x1 2, x2 6, and the objective function value or the z value is 36. We have remaining 2 more examples. Example 2, I will not show you what the solution, but if you want to do it, you're gonna find out that the solution is unbounded solution. Example 2, the solution is unbounded solution. Now, I want to do the example number 3. Example number 3. So example number 3, we have minimization, right? And 5 constraints. Okay, please do it, and I will show you what the solution. Number 3. Okay, finished. So, what's the answer? Okay, let's do it together. So nothing much, it just have more constraint, okay? Everything's just quite the same step. So first, I'm construct the axis, and I think the scale around 10 is enough for this problem, okay? So then we start with drawing the graph of all constraint. The first constraint, 3x1 plus 2x2 less than or equal to 18. Again, we try to find x1, x2 intersection. So in this case, for the first constraint, is cutting x1 is at 6, cutting x2 at 9. Right? It's going to be like this. And since it's less than or equal, so we're going to shading below the line. Right? This is the first constraint. For the second constraint, x1 plus x2 greater than or equal to 5. So we draw in the graph of x1 plus x2 equal to 5 first. So this is 5. Right? So it's cutting both 5. Cutting x1 at 5, cutting at x2 at 5. And since it's greater or equal, okay, so we're shading above the line. So this is a second constraint. Right, we're shading above the line. What next? The third constraint, x1 less than or equal to 4. So this is the graph of x1 equal to 4. Less than or equal, we go to this way. How about the fourth constraint? X2 less than or equal to 5. So this is the graph of x2 equal to 5. Less than or equal. So we shading below the line. Let's say number 4. Then we go to the last one. Okay, this is the constraint number 5. Let's see here. Right? It's just in a different form. Right? Not the normal one. So how do we handle this? What are you going to do? Just multiply, switch, modify. Yes? You're going to have 8x2 less than or equal to red x1, right? In the case that you want more, the same pattern as other, you can have 8x2 minus 7x1 less than or equal to 0, right? But one thing that you can notice is about this constant value is 0. So it's just not the normal that you're drawing as usual, right? Because if you try to find x1, x2 intersection, you substitute x2 to be 0, you have x1 cutting at 0. You substitute x1 to be 0, you have x2 cutting at 0, right? Because the linear line that have the 0 constant value is going to be the guarded out of the origin point. But we need to draw in this line. One point that for sure that we know is about 0, 0, that this linear line passed through. We need to find another point and then we connect two points together, we're going to have that linear line. So another point is very easy. You just substitute whatever be the value of x1, and then you can get that cutting point. For example, if you substitute x1 to be 1, x2 you're going to have 7 over 8. If you substitute x1 to be 2, x2 you're going to have 14 over 8, right? But it's look weird that you have the fraction here. So I might prefer the integer value to make it more easier when we drawing the line. So if you substitute x1 to be 8, actually, what value do you get for x2? Have x2 to be 7. So for sure that 0.87 is going to be the one point that this linear line passes with, and it's easy to draw in. You can use another point. You can use any point that you substitute 7 over 8 to 14 over 8. That's fine. But for me, I prefer integer 8, 7. So then x1 8, x2 gonna be 7. So here, this is x1 equal to 8. And this is x2 equal to 7. Now this one is 7. Right? And then we're drawing this graph. Sorry. Something like this. Something like this. I don't know it's gonna pass that point or not because it's not just the exactly scale, but just the graph. But anyway, we know this is the graph for the fifth constraint. My question is shading below or above the line? Shading below or above the line? Come on, this is like a, not high school, but before high school. Math. Shading below or above the line? If you are not sure, it's possible, we don't know, because you're getting older and older, so your ability of the calculation is lower and lower. It's just normal. So if you're not sure, what you're gonna do, you don't know which side that you're gonna shading, right? Suppose that. Just pick up one point and substitute to see which side is the real one. For example, in this case, let's say that I think this is line, right? I just try point x1 8, x2 2, this point. x1 8, x2 2. Now this one. This point is below the line, right? Right. This point x1 8, x2 2 is below the line. So I'm still look at this for percent of 5. x1 8, x2 2. You can have 2 over 8 less than or equal to 7 over 8. Is correct? Yes, it's real. 2 over 8 is less than 7 over 8, right? So it's real, so it means we need to shading below the line. This is concept number 5. So then we try to find intersection area from all the constraints. And you can know that about this triangle, maybe, I don't know, not exactly triangle, but this product. This is a visible area. Right? And what next? We need to substitute some value to be the objective function value, right? So You can substitute any value. You can using 12, 24, something that you make it easier to drawing. But let's say that since I want to explain you more clearly, so let's say that I'm using, I assume Z to be 36. 36. Are you with me? Because the next class and the class after that and more week is more difficult. This is the easiest one this week. But not kidding, this is the fact. This is the easiest one for this course, the first week. Okay. So let's say that I assume Z to be 36. I'm going to drawing this graph of objective function to be my iso cost line. I try to find x1 intersection, substitute x2 to be 0. I have 4x1 equal to 36, x1 cutting at 9. x2 intersection, substitute x1 to be 0. I have 6, x2 equal to 36, x2 cutting at 6. So this is the graph of my iso cost line. Have the equation 4x1 plus 6x2 equal to 36. And then what next? We're using the ruler cover the line, right? Problem is minimize or maximize? Minimize, right? Minimize be project into direction that coming to origin point. So then, when you move the line, project the line, the last test point of physical area that we can contact is this one. Before the line is out of physical area. Okay? From here, you project to this direction. This is the last test point before the line is out of physical area. So the answer or the optimal solution point is this one. This one. Optimal point. And based on this optimal point, actually, we can know about the coordination, right? Immediately. Because at this point, x1 for sure would be 4. Right? This point, x1, 4, right? Now this comes from constraint 3, that's constraint 2. Constraint 3 is x1 less than equal to 4. This is x1 equal to 4. Right. And this is the intersection point between constraint 3 and 2. So you substitute x1 equal to 4 to constraint number 2. If x1 4, x2 can be 1. Right. So finally, the optimal solution is 0.41. So in this case, for this problem, you're going to have x1 equal to 4, x2 equal to 1, and z equal to 22. Are you with me? It's gonna faster and faster, okay? Because if you have any question, just raise your hand and ask me right away. So that I'm gonna move on. Okay, this is example 3. Example 4 is the same. Do the same way. I will not show you about the solution. Example number 4, the same way. Now everyone go to the last example of today. Please do example number 5. This is the top video exam level. Example 5. Please do example number 5. This is the last one. And don't forget to grouping, forming your group, right, in course build. Okay. You can see that for this problem, it's quite the same as previous one that we have 5 constraints. So just a little bit different that the constraint we have negative value, like just nothing much. But the one big thing that different from all the previous example is about objective function. You can see objective function we have the negative coefficients. Right, so it is not the normal one. Okay, let's see. So based on all the constraints, I think the scale around 5 for each side is enough to drawing the graph. Let's do the first constraint. Minus 4x1 plus 6x2 less than equal to 9. It's probably drawing the graph of 4x1 plus 6x2 equal to 9 first. We try to substitute x2 to be 0. We have minus 4x1 equal to 9. So x1 cutting at minus 2.25 is around this one. And for x2 interception, we substitute x1 to be 0. We have 6x2 equal to 9. x2 cutting at 1.5. So then we connect it together. It's cutting x1 axis at minus 2.25, cutting x2 axis at 1.5. And since this is less than or equal to 9, right? So probably I think the graph is going this way, shading below the line. So if you confuse, you can ask the question. No. The second constraint, x1 plus x2 less than or equal to 4. Similar, we draw the graph of x1 plus x2 equal to 4 first. So both cutting at 4, right? And it's less than or equal, so we shading below the line. This is constraint number 2. The third one, 4x1 minus 2 greater or equal to 0. So if you move minus 2 to another side, then you move 4 divided. So you can have x1 greater or equal to 2 over 4, right? Or 1 over 2. So it's around here. 0.5 greater or equal to 0. So we go to this way. Constraint number 3. x1 greater or equal to 1 over 2. Constraint number 4. x1 less than 2 to 5, x2. This is the same as the previous example, right? That going to be the graph that out of the origin point. So one point that this graph going to pass to is about point x1 equal to 5, x1 equal to 1, x2 equal to 1. Right? Constraint number 4. It's about the same as this one graph that out of the origin point, right? One point that this graph going to pass to is about x1 equal to 5 and x2 equal to 1. 5, 1. because if you substitute x1 to be 5, x2 is going to be 1, so it's made real. So 5, 1 is down here. This is x2 to be 1, this is x1 to be 5. So then the graph can be just like this. Past point 5, 1. And it's about the shading. So let's say that I have no idea. So I pick up point 1, 1 that above the line. I substitute x1, 1, x2, 1. I have 1 less than equal to 5, 1 less than 5 is real. So it will be shading above the line. This is graph of constraint number 4. The last constraint, x1 plus 2x2 greater or equal to 2, we substitute x2 to be 0, x1 cutting at 2. Substitute x1 to be 0, x2 cutting at 1. So this is a graph of the constraint number 5. And greater or equal to 0, we shading above the line. This is constraint number 5. Then we try to find intersection area of all constraints. It's going to be an area at the center. So the next step is we assume the value of objective function drawing the graph of iso cost line. So let's say that we assume z to be 10. So we're going to have objective function 2x1 minus 5x2 equal to 10. x1 interception, we substitute x2 to be 0. We have 2x1 equal to 10. x1 cutting at 5. Here. x2 interception, we substitute x1 to be 0. We have minus 5, x2 equal to 10. x2 cutting at minus 2. So this is the graph of iso cost line that has an equation 2x1 minus 5x2 equal to 10. So it looks different from when you compare to all the previous examples. This is because the coefficient in front of x1, x2 is negative. In this case, coefficient in front of x2 is negative, it's not positive. But it doesn't matter. We still apply the same concept. So in this case, once again, this is our iso cost line. We're using the ruler cover the line, right? And this is 0, 0, right? Problem is minimize or maximize? Minimization. Minimization, we move to direction coming to the origin point, right? Remember? Origin point is right here. So we cover the line. We move to this direction. But we not stop at origin point. Because we can go further. We still have the area to go. Remember that we're gonna stop at the point that provide the last one that the iso cost, iso profit contact before it's our visible area, right? So in this case, if you project to this direction, coming to the 0, 0, optimal solution will be at this point. So this is the optimal one. And we can find the coordination. This is about the cutting point between constant 1 and 2. Okay, look at this. It's cutting point between constant 1 and 2. So if I using 4 multiply for all constant 2, we can have 4x1 plus 4x2. This one to be 16. And then I'm using the constant 1 plus. We're going to have 10 x2 equal to 25. So x2 is 2.5. If we substitute x2 to be 2.5, x1 going to be 1.5. So this is the coordination of the cutting point. x1 1.5, x2 2.5. So in this case, the answer x1 is 1.5, x2 is 2.5. And if you look at z value, you're going to have 2 multiply 1.5 minus 5 multiply 2.5. So then you have minus 9.5. Is this correct or not? Z equal to minus 9.5. Is correct. As I mentioned, just decision variable that cannot be the negative one. The z value objective function value can be negative. Right? Okay, we finished. I believe that some of you might be curious or confused a bit about objective function line or the iso cost line. So I will gonna explain you more. Okay, look at this. Suppose that look at this. Normally, let's say this is origin point, this is x1, this is x2. If you have this constraint, look at this, 2x1 plus 5x2 equal to 10. You can see coefficient in front of x1 positive, coefficient in front of x2 also positive. Both are positive, so it means when you drawing this graph, it's going to go like this. It's cutting at positive x1, positive x2. And as I mentioned, when we cover the line, maximization we project in the direction that out of origin point, right? Minimization we coming to the origin point. But I never said that you stop at origin point, remember? But in the case that you analyze in the first quadrant, for sure, when you analyze minimization, you might stop at origin point because it's the last point of the first quadrant. Or you have the 0, 0 here. So in this case, if you go to this way, maximization. You go to this way, minimization. Now, let's consider our example number 5. Right now we have 2x1 minus 5x2 equal to 10. You can see coefficient in front of x1 is positive, right? Coefficient in front of x2 is negative, right? So that's why it's cutting at, right? This cutting x1 positive, cutting x2 negative. But it doesn't matter because the concept that we apply is we look at 0, 0. If you move in the direction that out of origin point is maximization. If you move the direction that coming to the origin point is minimization. But don't forget that we're gonna stop to the point that to be our optimal solution point. When that point is the latest one that the isomorphic or iso-class line is contact before it's out of the physical area. So in this case, we go to this way, maximization, and we go to this way, minimization. So that's why in this case, when I go to this way, minimization, I will stop at this point because this is the latest one before this line is out of useful area. If I change the problem to be maximization, if I change this problem to maximization, the answer is going to be this point. Because you move to this way. The latest one is this. Okay. Two more. If I have another case, let's say minus 2x1 plus 5x2 equal to 10, what happens? Coefficient of x1 negative. Coefficient of x2 is positive. The graph is like this. Right? Cutting x1 negative, cutting x2 positive. Again, we look at 0, 0. You go to this way, minimization. You go to this way, maximization. This one mean go to this way next. Okay? And if someone might say that Ajahn, it could be wrong. Because listen carefully, look at this. I used to have some students said Ajahn, it could be wrong because if I substitute some value and I'm drawing the line for this problem and I have this line, let's say this line. Okay, this is my isopause line. I substitute some value and I draw this line. And this is 0, 0. You say that minimization, we look at 0, 0 and we move to the direction that coming to the origin point, right? So if there is no way this is going to be my optimal solution point. So I'm wrong. This means Ajahn wrong. Just wrong. So my answer is there's no way to have this case if you are a normal person. Why? Because if you are a normal person, when I ask you to substitute some value here to draw in this graph, you can assume positive or negative value. Positive. And you assume the positive one, just like this one. There is no way that the graph is above 0, 0. Because this graph, this one is negative. So there is no way they're going to have that case if you substitute the value to be positive. But yes, if you are the abnormal person, you said you want to be cool. You substitute this one is minus 10 because you don't want to finish everything early. Right? You want to give some effort. Yes, you might have this line, but everything's going to reverse. Okay? Finally, the last one before we finish. The last one. If look at this. If you don't understand anything that I've explained about this, don't worry. Just back to the basic. You might do some more work more than your friend. Just one more step. For example, you have no idea. You substitute z to be 10. We have this line, right? Then you try another value, maybe 15. You're going to have another line. And then you know that which side is going to be lower, which side is going to be the upper. Right? Because if you substitute 15, you're going to have the graph like this. So then you know that, okay, this is 10, this is 15. So it means go to this way is more profit. Go to this way is less profit. That's it. Just drawing two lines. Then you can know which direction that you're going to move to find the answer. Okay, this is another solution. Any question? Okay. No? So I assume that you don't understand anymore, or maybe you will understand. So, okay, nice to see you all again. See you next week. Please go back to make a review. Next week is a difficult one. Believe me. Okay? And thank you for your attention. That is for today.